My talk will be devoted to the hot functional approach, and the second part will be devoted to the Landgren-Monin-Novikov hierarchy of the equation for the multi-point PDFs. Here's the content of my speech. I will tell about the extension of group analysis towards functional differential equations, at least a special type of them. Then about application of this extended group analysis to the Berger's equation, to the functional formulation of the Berger's equation. It's not done yet for the Navier-Stokes, but Berger's equation is often considered as a toy model of turbulence. And then about the group analysis and invariant solution that were found. And next, I will switch to the Landgren-Monin-Novikov hierarchy and about statistical symmetries that were derived for them. So, first, I would like to start the talk with some ideas about treating turbulence as a stochastic field. We know that the turbulence, we have the deterministic Navier-Stokes equations, and when we have initial conditions, we know the solution, we can solve the solution. However, due to the randomness of, due to the dependence of turbulence on small variations in the initial boundary conditions, we can treat it as a stochastic field. And we call that the stochastic process can be considered as some generalization of the random variable. Stochastic process is additionally dependent on some, for example, on time. And stochastic field is dependent on time and on special variables. Now, we will use, in order to describe turbulence as a stochastic field, we use probability density functions. We know that the probability that a random variable is contained within V and V plus dV is described by one-point PDF function. However, to describe stochastic field, we need information about, we need the multi-point informations. So we need the multi-point PDF functions. I will here introduce also the idea of and the definition of the characteristic function. Now, if we have the PDF, endpoint PDF, or endpoint characteristic function, we can calculate statistics either by differentiation of characteristic function at the origin or by integration of the PDF. So these two approaches are equivalent. Now, the question is, what do we need to fully describe the stochastic field, the turbulence? We know that some classical models and to model turbulence, for example, eddy viscosity model, they provide only description of mean velocity. So one-point first-order statistics. Now here are the Reynolds stress models, which provide the second-order statistics. If we go up with the order of statistics, we have, for example, one-point PDF methods, which, at least theoretically, you can compute statistics of any order. Now, there are some two-point models that exist, although are rarely used. So it gives us only only limited information about turbulence. Now, if we increase the number of points, we go here with the number of points to the infinity and with the order of statistic to infinity, then we obtain the full description of stochastic field. And this can be done either by considering multi-point correlation equations, which Professor Oberlapp was talking about. And this is the infinite, there are the infinite number of equations. Or we can consider infinite number of equations for the endpoint PDFs functions. This is this Landgren-Monin-Novikov hierarchy. or we can consider only one equation for the Hopf, which was introduced by Hopf, for the Hopf characteristic functional. So in my talk I will concentrate on these two latest latter approaches. Now, the idea behind this Hopf characteristic functional approach was that if we go with the number of points to infinity, then the PDF becomes a probability density functional. That means instead of a set of variables v, we have, the continuous variable v depending on x. Now, the characteristic function also, in the same way, extended in the same way, becomes the characteristic function. Multi-point statistic can be then computed by taking functional derivatives at the origin. So the functional derivatives can be here considered as an extension of the gradient, in the sense that instead of differentiating with respect to this discrete s, we differentiate with respect to a function at the point. So the difference between these two descriptions, Navier-Stokes and Hopf, are that Navier-Stokes describes one realization of turbulent fields. So given initial condition, we have the solution. The Hopf functional aims to describe the ensemble averages of solutions. Now, the question was how to treat, we have this description, it is known for years, this Hopf functional description, and the question was how to deal with this. Is it possible to find any solutions of this equation, at least some special solutions? And we wanted then to use the Lie group analysis in order to get some mathematical, some insight into these equations. So first we had to extend the Lie group analysis from the partial differential equation for a set of variables v and the derivatives of phi with respect to any possible combination of independent variable up to the order q. Then when the number of independent variables increase to infinity, we deal with the functional differential equation, and we consider such symmetry transformation, so we look for new variables which doesn't change the form of the equation. The basic idea here is that the classical formulation for the classical parameter point transformation, and it's their extension to the continuum formulation. So the sets of variables were replaced by a continuous set, and also instead of the set of infinitesimals c, we have a function. Here it's a function of x. We extended also the definition of differential operators. Here, actually, the sum were replaced by integrals, and also the generator and its prolongation were also extended to this continuum case, as we call it. Now, in order to calculate infinitesimals, we had to solve such equation, and we obtained an overdetermined system of functional differential equations that had to be solved in order to obtain this infinitesimals cx and ct. And once we would have these infinitesimals, it would be also possible to obtain an invariant solution of the functional equation. So this extended Lie group analysis was applied to the Burgers equation in a Fourier space. It has such a form in the infinite domain, and the Hopf functional formulation of the Burgers equation has such form. So these are functional derivatives and the integrals inside. And the question was, is it possible to derive solution, to find solution of the Hopf equation with the use of the Lie group theory. When we solve this overdetermined system of equation, I must say that this we also don't know if it is a complete solution. And actually we find infinitely many solutions for the ck, but the corresponding solution for xt and eta were found only for two cases, and they are written here. One is for the invested case, which corresponds to scaling symmetry, and also for the viscous case. Here it corresponds to the translation in time and scaling of z with the k here. And although these sets of infinitesimals look simple, it was still possible to derive some I think, interesting solution I mean something non-trivial. If one considered viscous invested case, the key idea was here to that this system, hyperbolic system of equations, was true for each k. So well, this procedure was described in detail in our publication, in our recent publication. The idea was that this system of equation gave us infinitely many constants which have such form. We used such equation to derive the first constant. Then we properly reformulated it to obtain the second constant and so on. And so the general form of the constant Cn plus 1 has such form. And the solution was found as a sum of these constants. Also, going with this back to the functional equation, we obtain a relation between function fn plus 1 and function f, so the lower order. Now, if this is still the solution for the invested case, by functional differentiation, we can find here the mean of v, or second order second two-point statistics, and for example the energy. So what we recognize here was the 1 over t decay of the sawtooth profile, which is known as solution of the Verhes equation in the invested case. Now, for the viscous case, by doing analogous analysis, we found also the constants C, the set of constants, and we could also calculate the mean of V and higher order statistics. And here is we have the time decay of Fourier coefficients for large times, which was found also in some paper. The point is also here that a relation between function fn plus 1 and the lower function can be also found by introducing this solution back to the Hopf equation. So now to change the subject to the problem of multi-point correlation equation, to the equation for the PDFs. First, I recall that for the set of equations for the multi-point correlations, there were two symmetries, statistical symmetries found in the paper of Professor Oberlack and Andreas Rostek. The professor was talking in detail about this approach. Now, we did it now with the Lenin-Novikov hierarchy of equations for the n-point PDFs function, and this has such form. And the question was also, can we find any additional statistics? Can we find something analogous to the statistic found for the multi-point correlations? And we have to take into account also some constraints that has to be satisfied for the PDF functions. That is the normalization and reduction property, the continuity condition, and the coincidence property. So where the 2 points are becoming close to each other. This is important, especially because it's used for in the derivation of the Landgren-Monin-Novikov equation, and also a separation property. In order to find the statistical symmetries of the PDF, we presented first the PDF as a Fourier transform of the characteristic function, and we know from this multi-point correlation equations that the statistics of turbulence were translated or scaled. So it is possible to expand we expanded the characteristic function into the Taylor series, and we applied the same transformation to the moments here. And we checked if this is the symmetry, if this is also a symmetry of the equation for the PDFs. So for the translation symmetry of the correlation, we have found an analogous translation symmetry of the PDFs, which have such form in order to also satisfy these constraints of the PDF. And where this function phi, actually the integral is important, that the integral of this function phi has to be 0. And what this symmetry meant, and what such transformation means. It is the example, let's consider a PDF, which is first, for example, maybe first symmetric, and then there's some function phi, which is the integral of which is 0. But in order to give the translation of all statistics, this function must be non-symmetric. So this is what we obtain after the transformation, and we see that we obtain from the initially symmetric function, we obtain a function which has non-zero higher order statistics. So this also explains us, this is a link to this symmetry of this multi-point correlation equations, and tells us how such symmetry influences the instantaneous, the fluctuation of the instantaneous velocity. It simply changes the form of the probability density function. Now, the second was the scaling symmetry. So, if we scale here the moments in the Taylor series extension of the characteristic function, we obtain, and we go back to derive, to calculate the PDF, we obtain such a scaling symmetry for the PDF. And the important was here that the integral of PDF still has to be 1. And how this symmetry looks like, we have some PDF function, we subtract delta function, then we scale it by some factor, and then we add again a delta function. What we obtain here actually is such a PDF, which is the PDF, we obtain such a PDF by measurement of the intermittent signal. It means the signal which is when we have laminar turbulent flows, we have fluctuating signal, and then for some time constant. So this is how this scaling of the statistics manifests itself in the PDF functions. So to compare these 3 different approaches and to sum up maybe these considerations, we have the multi-point correlation equations with the translation symmetry in the Landgren-Monin-Novikov hierarchy, we found such corresponding translation symmetry. And this symmetry also can be found, the correspondence can be found in the Hopf functional equations, but in this case we have a solution, and we have here this function f, and we can show that the form of this solution doesn't change if we transform the functions, this function here inside the integral by in such a way, and then we obtain also for the, if we compute statistics, we obtain also the translated statistics. For the scaling symmetry, we have scaling in the multi-point correlation equations. Then we found the scaling in the Lambda non-Novikov hierarchy, and also the scaling can be found for the characteristic function or characteristic functionality. So, to sum up, I would say that the new mathematical formulation may give some new insight into the investigated phenomenon, like here was the phenomenon of turbulence, and the group analysis was extended towards functional differential equations. We obtained some special solution of the Verhes equation, and in future also Navier-Stokes equation can be studied. And also there are apparently the statistical symmetries are present in the Landgren-Novikov hierarchy, and the role of this new symmetry transformation may be investigated in future.
So, thank you. Questions? Okay, my question. It's well known in white subject like turbulence. So, did you find something new compared with Frisch and company for Burger's equation?
No, actually, because it is, I mean, this solution, what I shown is quite, it was obtained not long time ago, and especially in this, I said that we obtained some correlation between the function f and the lower order functions. So this is, I mean, this is as a next step to compare it with the, for example, results of simulations or other. I mean, it's not fully exploited this form of solution yet, but it's a direction of the investigation.
Okay. So, what more questions?
Maybe I can give a comment. I mean, you probably didn't recognize, I mean, the paper we published on the extension of Lie symmetries applied to functional equations. It was published 2006. And then for a long time, we had the machinery there, but when you apply it to an equation, it became so complicated that we gave up. And only very recently, when we started a year ago or so, right?
The problem was more, I mean, to derive some solution which is not trivial out of this.
Because
it was more technical problem.
Yeah.
They have these functional equations, you know, very difficult to treat.
Yeah, I know. But as suggestion for next research, you know, for example, if a system of ordinary differential equation, we go higher, we consider Liouville equation, right? But the same way for partial differential equations, we can consider functional equation like Liouville analog for partial differential equation. So you can try to find symmetries in this case, and maybe simplest case when main part, so I don't know if we have small parameters, is ordinary differential system. In this case, easy to research. So
Maybe you have one more comment.
yes.
There was this question about the Kolmogorov behavior. I mean, what you see in particular, we have this one symmetry that tells us something about intermittency, which is usually referred to as the main reason why Kolmogorov doesn't work for the higher orders. And also, skewness, flatness, and these things are essentially due to one of the symmetries in the PDF. So we believe now we have the machinery there, but still, you know, to solve it completely is probably at least a long way.
So
But I see that symmetries are important, absolutely crucial for the understanding of the statistics. That we definitely see.
So I see if in low order we have symmetry, some symmetry like for Kolmogorov solution, but in high order symmetry is destroyed or change solution because we have intermediate, for example. It's a different situation. So we wide picture, right? Or I don't know.
Yes, I mean, because all the classical symmetries were also are present in the equations. So this is only that using this full approach, we have more information, and so we have
more detailed.
And when it contains the statistics, which yes, Navier-Stokes equation. If you consider you only have instantaneous field there. So if you consider such a formulation of the problem where you have all possible statistics, and this is called a closed formulation, then there is a hope to find something new. And also we still don't know if this is complete. What this is. Maybe there are more, for example.
But no, I mean, if I have system, if I have reduced system, I hope I will have more symmetries, more detail, more simplest sum. And but if I have more details, less symmetries, right? No, in this for turbulence the same.
No. In this case, we get for the turbulence we get many more new symmetries.
Yeah, I see. So you definitely more symmetries. So this is contradict my general opinion, but no, not only my, but general opinion.
I think it follows from the fact that you have the solution of the instantaneous. Here you treat only instantaneous for the Navier-Stokes, and here you have statistics, which is you said that there are more symmetries.
You cannot really say that the statistical equations are easier. I mean, you're saying, well, Navier-Stokes has so many. You go to a plane case, you have more symmetries. You can, the simpler the system, the more symmetries you get. Here, you can't really say that because, in a sense, the system is much more complex because it's functional. But still, we get many more symmetries.
But in general question, so you can apply this technique for example, diagram methods also, where no
Say that again.
Diagram.
That we have never tried.
Different approaches for turbulence description.
Yeah,
you know.
They use that for the Hopf. Yeah. I looked at it a long time ago. There is one book they describe it. That is some in the 80s. Some Czech mathematician. But we never looked at it in detail.
Oh, yeah. So, great. So, more questions? No questions. So thank you again.
Yes, and some comments. I'd like to say that this work was started about 8 or maybe 9 years ago. Yes. So just and this is absolutely new result concerning of such a general object as a functional as the equation in functional differential derivatives. Because as we know that for the present time there is no result concerning how to investigate of equation of this type, and moreover how to find a solution of such general type of equation. So just and this work it's possible to see on this result as a first mathematical studying a first mathematical result in this direction, especially if, because we know that at present time there is no any mathematical result concerning equation in functional derivatives, how to resolve and so on. But nevertheless, I'd like to attract your attention to this book, this one, Asymmetry of Integrated Differential Equation, that's published 3 years ago, where it's also considered asymmetry of the equation, asymmetry in the form of a non-local, in non-local form, and the other used a prolongation with respect to variation of the function in infinite dimensional functional space, and maybe here is some correlation just in this book.